I have just checked it down. I am live. You can see here. This is the page for live streaming. So here you can see this is here it is showing that end stream, which means that we are live. So if I end this stream, then I will not live. Yes, yes, this is live link. Fluid mechanics part 4 I am discussing right now. Okay, okay. Just a second. So is the screen is visible to you now? Okay. So what I'm discussing here is that here the rate of flow of mass is not constant because mass is continuously decreasing as it goes down. So mass is continuously flowing out. So this could be our rate of change of mass dm by dt into v. Okay. Now this mass you can write as F is equals to d by dt density multiplied by volume into velocity. Now this volume you can write area A, this small a, because mass is coming out from this. This is small a into velocity. This will give you the volume flow rate. So this finally will become rho into small a into velocity into velocity. So the force here that we have is rho a v square. Okay. Now this is the force applied by the liquid on this vessel. Now if this force, because we want to know the minimum coefficient of friction necessary to prevent sliding on the vessel due to impact force. So if this force is just greater than or equals to the frictional force provided by the surface, in that case, this friction will prevent the sliding of it. for the maximum value of it. Okay, just a second. Should be less than or equals to. F here is frictional force should be greater than or equals to rho a v square. Okay. F is nothing but mu n, or n is equals to mg, is greater than equals to rho small a into v square. Now we know that from the formula of, or the for the Torricelli's law, what we can conclude, that v is equals to root 2 g h, and h is the, let's say, height above. Okay, this is h height up to which this liquid is filled. Now so v square will become 2 g h. Now mu, mass you can write, rho, volume will be area capital A into height h up to which this liquid is filled, into rho A is equals to rho A 2g h. On the next page I will do it. So it is mu mg. M you can write density into volume. Volume of the container is area. Volume of the liquid inside the container is the base area multiplied by height multiplied by g. Okay, is greater than, so greater than equals to what, rho a 2g h. Now you can cancel out rho, g, and h. So finally what do you have? Mu into a capital A is greater than or equals to a 2 into small. Now mu is greater than equals to 2a by capital A. For minimum value, for minimum value of mu, this should be equals to, because all the values rather than equal, other than equal value, all the values of mu is greater than 2a by a. So for mu minimum, is equals to 2a by capital A. Okay. Got it? So this is the minimum coefficient of friction that we should require to prevent this vessel slide on this surface. Option C is the correct one. Okay. Now, the next question is this. So student of JNB Bhavnagar, are you here? So if you are here, try to solve this question, and I'm giving you 2 minutes to solve this question. Now, in this question, you have to find the time to empty the tank filled with liquid up to height h. So this is capital H, up to which the liquid is filled. This height initially, and the area of hole at bottom is A. This here is of A, and area of cross section of the base is A. So this base area is capital A. Now try to solve this question. I'm giving you 1 minute. So if you are here, please type yes in the chat box so that I would know that you are here. Okay. And you are listening to me. Okay. So as you are not responding, I am considering that you are not solving this question. So don't worry, I will solve it for you. Okay. So initially, up to h height, the liquid is filled in this container. Now we are considering that after some time, so let us consider after some time, or after some time means after time t, the height of the liquid is inside the container, height of the liquid inside the container is y. Okay. So we can say that at that particular time, according to Torricelli's equation, the velocity of the flow will be root 2 gy. Okay. Now, this is the velocity. Now, we are interested in time, that how much time it will take to fill out or to empty the tank. Okay. This V you can also write as, this is equation number 1. Now applying equation of continuity. Okay. Because now for after time t, the height will be here is y. Okay. And this is not constant. This is continuously decreasing. So we can say that A1 V1 is equals to A2 V2. A1 we will take the area of this surface, which is capital A. V we will take, V1 is the rate of decrease of this height, dy by dt. And this is decrement, so we will take it minus. Now A2 is small a and V2 is root 2 gy. Now here you can see that it is minus dy by dt is equals to small a by capital A root 2 gy. Okay. Now this is dy here and this is root 2 gy. So we will take this function below this. So it is minus dy by root 2 gy is equals to small a by capital A into dt. Now if you integrate it from 0 to capital time t, okay. So at time t is equals to 0, the height of the liquid is capital H, and at time capital T, when the tank is empty, the height will become 0. Now to remove this minus, you can reverse these limits. Okay. So what you can do, you can make 0 to h dy by root 2 gy is equals to small a by capital A into dt. So this you would remember the integration a to b of fx dx minus fx dx will become integration b to a fx dx. Just inverse the limit. Okay. Now this 1 upon root 2g is constant. So we can take it out. So 1 upon root 2g integration 0 to h 1 upon root y dy is equals to small a by capital A into et. Okay. Now 1 upon root 2g into this will become y raised to the power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1 0 to h equals to a by capital A dt. Okay. Now this is 1 upon root 2g. This will become y raised to the power half and this will become half. So this 2 will come in numerator. So it will become 2 root y 0 to h. Now we are putting and here also we forgot to mention here. This will be 0 to capital T dt, 0 to capital T dt. So this will become a by capital A into capital T. Now 1 upon root 2g, 2 root h minus 0 is equals to small a by capital A into time t. So this will become 2 capital H by 2 you can also take inside. So it will become 4, 4h upon 2g small a by capital A into t. Time you will have as capital A upon small a into 2h upon g. So this is the time taken by the liquid to empty the tank. Okay. So I hope you got this. If you got it, and if you have any kind of doubt, you can ask right now. But this is the question we have. Okay. Is it clear to you? If it is clear, please write this thing in the chat box. No? Okay. Now, this one. The pressure acting on a submarine is 3 into 10 raised to the power 5 Pascal at certain depth. If the depth is doubled, the percentage increase in the pressure acting on the submarine would be. So this is very simple question. Try to solve it giving you 1 minute. Okay. The pressure at certain depth is given to you. It's 3 into 10 raised to the power 5. If the depth is double, then what is the percentage increase in the pressure acting on the submarine? Atmospheric pressure is given to you 1 into 10 raised to the power 5. And density of water is this. Now, let's say our submarine is at, let's say this is at height or depth h from the free surface. So the pressure acting on it will be P atmospheric plus rho g h, and which is given to you as 3 into 10 raised to the power 5 Pascal. Okay. So rho ATM is become 1 into 10 raised to the power 5, which is given to you, multiply by, sorry, plus rho g h. Now this you can cancel out. So this is 3 into 10 raised to the power 5. This is 1 into 10 raised to the power 5. So rho gh you will have as 2 into 10 raised to the power 5. Now rho is given to you 10 raised to the power 3. G is 10. h, 2 into 10 raised to the power 5. This will become 10 raised to the power 4. It will cancel out 4 power. So height that you will get is 20 meter. Now it is very simple. Height h dash is doubled. So it will become 2 into 20 will become 40 meter. Now the submarine is at 40 meter down. So what is the pressure at that? So P atmospheric plus rho g h dash. So it is 1 into 10 raised to the power 5 plus 10 raised to the power 3 into 10 into 40. So this will become 4 into 10 raised to the power 5 plus 1 will become 5 into 10 raised to the power 5 Pascal. This is the new pressure. So percentage increase we will give by P final minus P initial divided by P initial multiply by 100. This is the percentage increase in change in pressure. So this you can say P final is 5 into 10 raised to the power 5. P initial is 3 into 10 raised to the power 5, which is given to you. So this will become 2 into 10 raised to the power 5 divided by P initial is 3 into 10 raised to the power 5 multiply by 100. So this will cancel out. This will become 200 by 3%. So this much is the increase in the pressure of the submarine acting on the submarine. Okay. So 200 by 3. Now, I hope you got it clear. If you have any kind of doubt in that question, you can ask. Now, a small hole of area of cross section 2 mm square present near the bottom of a fully filled open tank of height 2 meter. Taking G is equals to 10 meter per second square, the rate of flow of water through which the open hole would be nearly through the open hole. So it's a very simple question, yet very conceptual. So this is the open tank that we have. If the tank is open, so the pressure acting on the tank is only atmospheric pressure, P atmospheric. At the bottom, nearly at the bottom, we have a hole from which the water is coming out. Okay. So according to Torricelli's law, according to Torricelli's law, what it has been said that if the tank is open, so the velocity of outflow or reflux is given by root 2 gh, which is h is the height above the hole that we have made. Or you can say h is the depth at which the hole is present or orifice is present. Okay. Now, this is equals to the height up to which the liquid is filled, which is given to you 2 meter. So h here is 2 meter. So V you can already and easily calculate it is 2 into 10 into 2. So this will become square root of 40 meter per second. But this is not our answer. In the question, in the answer you will see it is meter cube per second, meter cube per second. Meter per cube per second is the volume flow rate it is interested in. So for volume flow rate, is given by area through which the liquid is coming out multiply by the velocity. Area is 2 mm square, which is 2 into 10 raised to the power minus 3 meter into root 40. Okay. Now, if you able to calculate this, just a second, give me a second. It will become square root of 40 will become 6.32 and multiply with 2 also. So it will become 12.6. So 12.6 10 raised to the power and it is mm square na, so this will become 10 raised to the power minus 6. Minus 6 meter cube per second. So this is the answer, option D. Okay, I hope you got it. Now, move on to the next question. This one. Okay. So in this question, the terminal velocity of a copper ball of radius 5 mm falling through a tank of oil at room temperature is 10 centimeter per second. If the viscosity of the oil at room temperature is 0.9 kilogram per meter second per meter per second. Okay. The viscous drag force is. Okay. So firstly, we will write what is given in the question. Given that terminal velocity v is given by 10 centimeter per second. So we have to convert it into meter. So 10 into 10 raised to the power minus 2 meter per second. Radius of the copper ball is also given you 5 mm. We will also calculate it in terms of meter. So 5 into 10 raised to the power minus 3 meter. Now, one more information is given to you as viscosity of this oil is given to you, or this is nothing but the coefficient of viscosity, eta, which is given to you 0.9 kilogram per meter second. Okay. Now, all you have to calculate is viscous drag force. So we know from Stokes law, viscous force or drag is given by minus 6 pi eta r into v. Now, minus 6 pi you can write 22 by 7. Eta you can write zero point 0.9. R is given to you as 5 into 10 raised to the power minus 3. And V is given to you as 10 into 10 raised to the power minus 2. Okay. So all the data is given to you. Just you have to multiply and divide. So it is 6 into 22 into zero point 0.9 multiply by 5 multiply by 10. And this all is divided by 7. So it will become 848 divided by 0.57 multiply by 10 raised to the power minus 5. Now, if you take the decimal up to this point, 8.48, you can cancel out 2 power into this. It will become minus 3. So this option is the correct option. This is the viscous drag force which the fluid apply or this liquid apply on this copper ball. Okay. Now, this question. Try to solve this question. A drum placed on a floor is filled with a liquid of almost no viscosity, which means the viscous force here has no interest. So no viscosity to a height capital H. So this liquid is filled up to a height of capital H. Now, a small opening is made at a height H from the base. From the base, a small opening is made at a height H from the base. So here is the base. And this is the small opening that we have at height small h. So this height would become capital H minus small h. The liquid jet strikes the floor at a distance x from the wall of the drum. Then find out the maximum value of x. So this liquid will fall out at this and strike the ground from the bottom of the tank at a distance x. So we want to know that what is the maximum value of this x. Okay. So firstly, what we are going to do, we are going to calculate the velocity of this liquid which is coming out. From that velocity, if we multiply it with the time it will take to come down, so we will have the value of x. So according to, because this is the open tank, so according to Torricelli's law, the velocity of outflow is given by root 2 g, and this height would be measured from the free surface of the liquid. So this is the free surface up to which at which depth the hole has been made. So this depth is capital H minus small h. Capital H minus small h. Now this is similar to if this is a velocity v and this a height h. So it will cover a range, let's say r here. So r is nothing but time to calculate this r is, because at this particular point of time this height is vanishes. So we can apply Sy is equals to Uy into T plus 1 by 2 Ay into T square. Now this velocity is 0, and this Sy also is h, and finally it will become 0. So it is 1 by 2 times g into T square. So time it will take to come down is equals to square root of 2h by g. Now remember in this height is measured from the bottom, from the ground. So here this height will be measured from this bottom. So this height would be considered at small h. So time taken to coming out will be root 2h by g. Now range x is equals to vx into t, because there is no acceleration in x direction. So x here is equals to vx value we have root 2g capital H minus small h into time 2h over g. Now this root g and root g you will cancel out, or I will cancel it out on the next page. Just a second. This is 2g and this is g. So x we will have 2g capital H minus small h divided by into 2h over g. So this g and g will cancel out. So finally what do you have? You have x is equals to square root of 4 small h capital H minus h. Now only h can vary. You can vary this where to place this orifice. Okay. So if you differentiate for maximum value of r, for maximum value of x, what you can do? You can differentiate this with respect to small h and put it to 0. Okay. So dx by dh, what it will be? Now, firstly, it will behave as a square root function. So dy dh, if you multiply 4h inside, so it will become 4 small h capital H minus 4h square. So firstly, it will behave as square root of this. So differentiation of root x type of function is 1 upon 2 root x. 1 upon 2 into 4 small h capital H minus 4h square. Now differentiate this inside function, which is 4h capital H minus 4h square. So it will become 4 capital H minus 4, and h square will become 2h. Differentiation of h square. So it will become 8 small h. And this would be equals to 0. So this vanishes to 0. Finally, what do you have is 4 capital H is equals to 4 capital H is equals to 8 small h. Now, you will have h is equals to capital H by, this is the value of h for which the range would be maximum. Now, this put this capital H by 2 in place of small h in this expression. So, x maximum you will have as 4 capital H by 2, h minus capital H by 2 will become h by 2. So, this 2 and 2 will cancel out. X maximum is equals to capital H. Okay. So, this is the maximum range for a liquid that is coming out from a hole which is made at h by 2. Now, this question is from surface tension topic. So, the amount of energy required to form a soap bubble of radius 2 centimeter from a soap solution is nearly. Okay. So, we know that surface energy is that energy that we require to form the soap bubble. So surface energy is given by surface tension multiplied by area. Now here you need to be careful about the when you are putting the value of area. You have to check whether this is a bubble, air bubble inside the liquid, or it is a liquid drop, or it is a soap bubble. So if it is a soap bubble, then this has two surface area. So you have to multiply this area by 2. So hence that we have soap bubble here. For soap bubble, this will become 2 times surface tension multiplied by area. Now, surface energy is 2 into surface tension is 0.03 Newton per meter. Area is, because it is a bubble of spherical shape, so it will be 4 pi r square, and radius is given to you 2 centimeter. So you need to convert it into meter. So this will be 4 into 10 raised to the power minus 4. So this whole will become as 0.06 into 16 pi 10 raised to the power minus 4. Now 0.06 multiply by 16 multiply by pi. So you have 3.01 10 raised to the power minus 4 joule. So that much amount of surface energy or energy you will require to form a soap bubble of radius 2 centimeter. Okay. So this is it from my side. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive. Okay, try to solve more and more question on this topic. If you find any trouble, you can connect me in the regular classes also. Okay, so thank you so much. Bye bye. Take care.